Children, today we are going to learn Arrhenius equation. The effect of temperature on reaction rate. This equation was proposed by Arrhenius. Arrhenius proposed its given note the explanation regarding to the effect of temperature. Generally, we know the reaction increasing temperature, certainly the rate has been increased. Okay, for example, when the hydrogen combines with bromine at 373 Kelvin temperature gives hydrogen bromide, and also the same reaction hydrogen combines with bromine at 473 Kelvin gives hydrogen bromide. Okay, both are same reaction, but the factor is temperature. Okay, so the temperature increased by approximately 100 Kelvin. Isn't it? When the time increased by the reaction, what would happen? To the rate of the reaction has been increased by 250 times. Okay, 250 times the rate will be increased. Okay, this is experimentally verified. For every 10 degrees Celsius, the rate has been increased 2 to 3 times. For every 10 degrees Celsius, the rate has been increased 2 to 3 Kelvin. Okay, for many reactions near the room temperature, the reaction rate tends to be double when the temperature is increased by 10 degrees Celsius. Okay, another one example, hydrogen combines with oxygen. What we get? Water, isn't it? Here, without temperature, nothing to be happened. Okay, so hydrogen react with oxygen, we get water. Okay, in the presence of electric arc. Okay, in the presence of electric arc. Without electric arc, nothing to be happen. Okay, we cannot get the water. Isn't it? So, this hydrogen combines with oxygen normally never gives water. In the presence of electric arc, the spark is produced now. Certainly the temperature is high and it fuses to get the water. Okay. Therefore, Arrhenius suggested that the rate of the reaction with the temperature. Okay. Okay. Rate constant K is directly proportional to the collision factor E power EA by RT. Okay, minus EA by RT is the collision factor. Okay, therefore we have to apply the another factor. This is another one factor, that is it's another one constant applied, that is K is equal to EA E power minus EA by RT. Okay, this A is the frequency factor. Okay, then taking natural logarithm on both sides. Taking natural logarithm on both sides. That is what we call natural logarithm. That is ln. Okay, natural logarithm. Therefore, ln K is equal to ln A plus ln E power minus EA by RT. Okay, so when ln E is equal to 1, therefore ln K is equal to ln A minus EA by RT. So here this ln E is equal to 1. So 1 power minus EA by RT, so we get minus EA by RT. Okay. Then ln k is equal to, just rearrange this equation, ln k is equal to ln a minus, so here is time, not a time is a small t, isn't it? So it's a capital T, that it denotes a temperature, so we have to take out in the temperature, therefore ln a is equal to minus a by r into 1 by t. Okay, then we know the straight line formula. What is it? Y is equal to mx plus c. Okay, y is equal to mx plus c. Therefore, we have to just rearrange the equation, that is ln k. Therefore, y-axis along the ln k. This y-axis along the ln k. Then the mx minus a by r 1 by t, then c is the ln a. Okay, therefore the intercept is the ln a, then x-axis, y-axis along the ln k, x-axis along 1 by t, isn't it? Then c is the intercept. Okay, therefore that is ln a. Ln a is the intercept. Okay, so here also we get a negative slope. Okay, that is m is equal to minus a by r. M is equal to minus a by r. Okay, this is the graphical verification. At time t is equal to t1, the rate constant k is equal to k1. At time t is equal to t2, the rate constant k is equal to k2. That means initially the temperature is t1 and finally t2. Initially the rate constant is k1, finally rate constant is k2. Okay. Therefore, we have to change this equation, that is ln k1 is equal to ln a minus a by rt1. Then ln k2 is equal to ln a minus a by rt2. Next one is comparing both equation 3 and 4. We get ln k2 minus k1 is equal to, so we have to cancel it, isn't it? So ln a and ln a both are cancelled. Okay, therefore what we get, the second minus first. Therefore this minus a by rt2 minus a by rt1. Therefore the symbol will be changed into plus. Okay. Now we get another equation, ln k2 minus ln k1 is equal to minus a by rt2 plus a by rt1. Okay, so here we take out the common factors. Take out in the common factors. Okay, so here this EA by R are the common factor in both. Therefore, and also we have to simply write this ln k2 minus ln k1 is equal to ln k2 by k1. Ln k2 by k1 is equal to A by R minus 1 by t2 plus 1 by t1, isn't it? Otherwise, t1 minus 1 by t2. Okay, both are same. Okay, just rearrange this equation. Is equal to A by R, then t1, t2, both t1 and t2 in the cross multiplication, so therefore we get t2 minus t1. Okay, next one, the natural logarithm change into the logarithm. Okay, therefore we have to apply the 2.303 value. Okay, therefore 2.303 log k2 by k1 equal to A by R. into T2 minus T1 divided by T1 into T2. Okay, therefore log K2 by K1 is equal to this 2.303 goes to here. Therefore EA by 2.303 R into T2 minus T1 divided by T1 into T2. Is it not? Okay. For this equation can be used to calculate the EA and the rate constant K2 and K1 at temperature T1 and T2. Okay, this is the Arrhenius equations. The effect of temperature on a reaction rate. Okay, hope you have understood. Thank you, dear students.